So the next talk is by Seiji Fujimoto, who is going to talk about the ALPINE-ALMA C2 survey, size of individual star-forming galaxies at redshift 4 to 6, and their extended halo structure.
Okay, so hi everyone, I'm Seiji Fujimoto. I got a PhD at the University of Tokyo last year and now working at the Cosmic Dawn Center in Copenhagen. So sorry, I will turn off the camera due to a potential concern on the internet. So yeah, but yeah. Okay. So yes, first of all, thank you organizer for this opportunity. And I would also like to mention that my talk today is one of the outcomes from the large Alpine collaboration, which was only possible owing to the great effort and leadership of our PI, Olivier Lefebvre. So along with my Alpine colleagues' talk and this entire conference, my talk is dedicated to his memory. So now I start. I have a bit updated the title. So today I talk about C2 halo in the early universe. So this illustrates the baryon cycling from the central galaxy to the circumgalactic medium, which is called cesium. So in this baryon cycling, the cesium metal enrichment is very important to understand the feedback mechanism from the central galaxy, which regulates the galaxy formation and evolution. However, if this system is too old and experienced many cycles already, it's hard to distinguish how each pure mechanism contributes to this metal enrichment. So investigating the cesium metal enrichment in the early universe is one of the key proofs to understand the pure feedback mechanism regulating galaxy formation and evolution. So recent ALMA stacking studies are capturing such earliest environmental pollution in the universe. In our previous study, we performed visibility-based stacking by fully making use of the ALMA archival datasets. The C2 line is clearly distributed beyond the dust continuum up to a radius scale of about 10 kilopascal scale, whose decomposed size even extended 5 times more than the rest frame UV emission. So we dubbed this large C2 line structure as C2 halo. Hydrodynamical simulation couldn't reproduce such large C2 halo structure, so these results suggest early galaxies eject an amount of carbon-rich gas far exceeding our expectation, and indeed, the C2 halo studies would be a helpful proof to understand the feedback mechanism of early galaxies in conjunction with theoretical studies. One obvious way to go is individual measurement instead of stacking. And another essential work is to understand what powers ionized carbon emission. This is because, the outflow is essential for the cesium metal enrichment, while once after it is enriched, the cause of powering the ionized carbon emission could be a different mechanism like photonization or inflow. So we have these two remaining questions. And now these two questions can be addressed by the ALPINE survey. ALPINE is one of the ALMA Large programs in Cycle 5 targeting C9 for over 100 main sequence galaxies at redshift around 4 to 6. The successful C9 detection offers us a variety of exciting studies, and in Olivier's paper, we did carefully classify the galaxy into 5 categories based on morphology and kinematics feature based on these large ancillary datasets. So from this classification results, here we select only isolated Alpine galaxy to remove potential effects on the halo emission from merging galaxies. And we also set some SN threshold to obtain reliable results. There are still remaining 23 Alpine galaxies. So based on this, we address the first question of the individual C2 halo. By the way, we performed the stacking analysis with this Alpine sample and confirmed the existence of the extended C2 halo. So it's good to know. But again, what we will address here is individual measurements. So in the studies of extended diffuse emission, the spatial resolution significantly affects the sensitivity. So the left panel shows the rest frame UV continuum map taken from HST after smoothing to match the resolution with ALMA. The red contour shows the C2 line taken from ALMA, and here shows the radial profile of the surface brightness of the C2 line and rest frame UV continuum. To obtain quantitative results, we define the intensity of the extended seeds emission beyond the smoothed beam size up to a radius of around 10 kilopascal scale, and regard the seeds halo as the object whose extended seeds emission is detected above 4 sigma level, while the extended UV continuum at the same area is below 3 sigma level. We find that 7 out of 23 isolated alpine galaxies are classified as the seeds halo object, including these two objects. So with the upper limit of the rest plane UV and also with the dust continuum, our previous study already showed that such high seeds line ratio over star formation rate at the outer halo area cannot be explained by the low mass faint galaxy. So now we would be able to say that we are identifying the seeds halo individually. During these works, we also identified a number of objects whose seeds line is not so extended in contrast. We regard those objects without seeds halo by setting the 3 sigma upper limit for the extended seeds emission and find mostly the same fraction there. When we compare with and without seeds halo object on the star formation rate and the stellar mass plane, we find that seeds halo objects are generally have the higher star formation rate and stellar mass values. So this difference might be just because the selection bias. So the brighter objects have brighter outskirt emission, which would be easier to identify. However, we realize that at least 3 seeds halo objects have similarly low values on this plane. And indeed, the left panel also shows that, this object might be faint and have larger error bar in the outer halo area, which makes it difficult to identify the seeds halo, but still the upper limit of the seeds line do not exceed the left plane UV continuum profile. So these results suggest that absence or existence of the seeds halo cannot be explained by the selection bias alone. So studying the difference of the physical property between with and without seeds halo object will enable us to address the second question of what is the origin of the seeds halo. So one clear feature we identified was the velocity offset. So all of our alpine targets had deep optical near-Earth spectra, and here shows the stacked spectra as a representative example. Not only in the stacked spectra, but we also analyze individual spectra, of course, and evaluate the velocity offset of the emission and absorption line features with respect to the seeds line emission. So first, let's see the Lyman alpha velocity offset. The red and blue histogram are the with and without seeds halo object. And the hatched one highlights the seeds halo object whose star formation rate are comparably low to the without seeds halo object. So we find that seeds halo objects generally have the higher Lyman alpha velocity offset, indicating more significant outflow expanding shell taking place in the seeds halo object. But more directly, we also find that higher velocity offset in the left plane UV metal absorption. So remembering this higher star formation rate trend, these results may indicate that seeds halo is related to the star formation driven outflow, which is consistent with the implication from the recent result of the spectrum stacking from much larger sample. Another difference we identified was equivalent width of the Lyman alpha line. So we find that seeds halo objects generally have the lower equivalent width value, indicating that this outflow might be dominated by cold neutral gas, or let's say multi-phase gas mixed with cold and hot, or firstly the hot gas was launched, but it became cold at some point through the radiative cooling. As a brief wrap-up of this slide, now we are addressing the second question. So the origin of the seeds halo might be the star formation-driven outflow, while we cannot rule out the possibility of the selection bias toward the luminosity object. But here I'd like to show some interesting cases well aligned with the star formation-driven outflow scenario. So one seeds halo object clearly shows its rotation feature beyond 10 kilopascal scale, and its rotation axis has a good agreement with the left plane UV major axis. So we performed the realistic 3D rotation modeling. So here the right panel is the best fit momentum one map. And so first of all, we obtain the effective radius of this rotating C2 gas disk is around 4 kiloparsec, which is around 4 times larger than the rest frame UV disk. So we might be witnessing the kinematics of the C2 halo, or let's say a large gas disk co-rotating with the central galaxy disk. So interestingly, when we take a look at the residual map, we identify a symmetric feature perpendicular to the main disk. So this may indicate that we are also witnessing the ongoing outflow, such like the famous picture of M82. The second case is that one C2 halo object also has extended structure in the dust continuum. Since the carbon exists at CGM, it is natural that dust is also there. But once after dust is pushed away from the center of galaxy, then it will soon become cold, so which is very difficult to be detected. But the extended dust continuum might be detected in some cases, such as powerful outflow cases. So where the extended dust still keep a good temperature, which we might be witnessing here. So indeed, this C2 and dust halo object has one of the highest Lyman alpha velocity offset and Lyman alpha equivalent with value among the C2 halo objects, even with the existence of the large amount of dust. So that strong outflow may help the Lyman alpha escape from this system. So I also touched some implication from the latest model in the last slide. So the recent semi-analytical model calculates the expected C2 emission in the cooling outflow process. In this model, the key parameters are mass loading factor and the circular velocity. And these the best fit parameter will reproduce the 10 kiloparsec scale C2 halo structure. Sorry that it seems that I don't have enough time to fully explain this interesting figure, but the likelihood for these two parameters are obtained like this. So if we obtain the kinematics of the C2 halo, we will directly get the circular velocity and easily constrain the mass loading factor at the same time. And this C2 emission in the outflowing phase is also confirmed in the hydrodynamic simulation, including radiative transfer. So this figure shows the time evolution of star formation rate, escaping fraction, and C2 and O3 line luminosity in the hydrodynamic simulation. So we can see that O3 line matches very well with the star formation, while C2 is more continuously emitted relative to the O3 emission, even in the outflowing phase. Where we also see this kind of the anisotropy between C2 and O3. But other simulation suggests rapid expansion of H2 bubble around massive stars. So the next way to go would be the kinematics of the C2 halo and multi-phase gas structure, which will provide strong constraint on the key mechanism in the feedback. And such ionized gas structure should be addressed with J-West genius spec IFU by targeting the rest frame optical line like H alpha and O3. Okay, so at the beginning of my talk, I told you the importance of the CGM enrichment in early universe, and now we are here. So C2 halo is identified statistically and now individually, but it's not always showing some trends. The possible scenario are just selection bias towards luminosity object or star formation driven outflow, but I would like to mention that even in the case the selection bias case, it means that C2 halo is universal picture in early galaxies, so it would be also very interesting. And the next step would be the multi-phase gas structure in 2D plus 3D up to the CGM scale, which will be one of the key proof to understand feedback mechanism in the era of ALMA and JWST. And in the last additional slide, I would like to mention how fruitful outcomes we have from Alpine survey owing to Olivier's great efforts and leadership. Also, I focus on the extended halo emission in my talk, but my paper also addresses the individual size and spatial offsets between UV and C2. So if you are interested on those papers, please take a look on archive. Okay, so that's it. Happy to answer questions.
Thank you, Seiji. We all miss Olivier for sure. We have very few, we just have a minute for a question.
Sorry for that, yeah.
There is a question. Thanks for the very interesting talk. Do you see outflow signature in stacked UV spectra, blue shifted absorption line, or of C2 halo objects?
So we identified the blue shifted absorption line feature, not only in the stacked spectra, but the individual spectra. So this figure shows the individual basis measurements. So yeah, that histogram shows the C2 halo object, and the blue shade is without C2 halo object, and we identify that more blue. So C2 halo object has a more blue shifted absorption line features.
Okay, there is another question. If you can detect dust in the outskirts of the galaxy, it could imply that the dust grains are not destroyed there, right?
Yes, yeah. So in this case, we identify very extended dust continuum up to similar scale. So dust grains are not destroyed there. Yeah, I think so.